Dr. Carroll, and this is a video about some examples of existing code and then making it parallelized. Let's jump in. The first example, let's look at matrix multiplication. We're going to look at it two different ways. Matrix multiplication has a very straightforward approach if we're just going to execute it on one processor, on one thread, and go through all of the respective elements of A, multiply them by B, and we get our matrix C. And we have this nested for loop approach here. And so if we wanted to just parallelize the loops, we could do that here. We need to watch out for a race condition. So let's see a different way of approaching it. You may know that you can divide up a matrix into different portions and then multiply those portions together to get a portion of the resulting matrix. And this has been looked at before with the divide and conquer approach to have 8 recursive calls to do matrix multiplication. Let's look at this briefly. We have our base case, not surprisingly. If it's just one element, then multiply those elements and put them in the resulting matrix. Otherwise, we're going to divide up the matrices into 1/4 parts because the dimensions are half and half in each direction. And so we can partition them up and then do our matrix multiplication here recursively to break this down. Well, you already might start to see how we could do this. We could leverage these recursive calls by every time we're ready to make a recursive call to spawn off a new thread. So let's go through this. We're going to need our base case again, but we're also going to need a temporary matrix to store the values so that we don't have a race condition. We can initialize all the values to D in parallel, and then we'll partition our matrices into 1/4 submatrices for both A, B, C, and D. The first 4 recursive calls are just as we did before, but we're going to spawn those off for a new thread to execute. The last 4, instead of having them write to the C matrix, we're going to write them to the D matrix so we don't have to worry about the threads contending and overriding each other and making sure that goes smoothly. Notice on line 17 we have a sync call here. We need to wait for all of the spawned threads to finish. And then once they have, then we can, in parallel, add up all the values of C and D and write them to the C matrix where we'd expect it. And there's matrix multiplication. And without loss of efficiency, we were able to do that, but we've leveraged multiple cores now to do it much faster. Let's talk about Mergesort. I love Mergesort. Here's the recursive textbook example of Mergesort. We have our base case. If we're down to 1 or 0 elements, then it's considered sorted. Otherwise, find the a midpoint and merge sort on the 2 parts of the array before the midpoint and after the midpoint, the 2 halves. And then when we're done, we merge all those together. Well, as you might have guessed, a multi-threaded solution here would have the recursive calls be spawned to a new thread to execute those. And then we need to sync up before we move on. Now, if we just parallelize that portion, the performance would significantly suffer. What's more interesting is how we parallelize the merge method here. So let's go into that. Let's start with the diagram. What we're going to do is we're going to take our A array and we're going to merge it into the B array, and then we'll copy B back to A. So we're going to start with A. And to be able to know what work can be done to break it up, we're going to find one value, and then we're going to know what portions of these original two parts of A are less than x and what are greater than x. So for the first one, P1 through R1, that's pretty easy. It's already sorted. We just can arbitrarily pick the middle one because that will guarantee that at least a fourth of the values over all of the values that are going to end up being merged into B are less than x, guaranteed. So that's really easy, very, very quick and simple to determine what x is and index Q1. Now for our other portion in A, we can utilize binary search so that we have a big theta of n to very quickly determine what is the index such that where all the values are less than or equal to x and where they are greater than or equal to x. So now with that information, knowing that, we know how many values there are. We don't know their relative orders, but we know how many there are. So then we know where x goes. And this is kind of magical to me. We assign x to B. Okay, so we know where it goes, and then we can spawn off a thread to say, okay, now I have these two sections shown here as an orange that are guaranteed to be less than or equal to x. Merge those. And I also know there's these other two regions, kind of a blue, where all the values are greater than or equal to x, and merge those. And so now we've divided it in roughly half, where we can say there's more work to be done now. We've divided it up so that we're not tripping over each other. Let's look at that in code. The actual parallel merge method here is really just a setup for our the recursive method that we're going to call here. Or I guess not recursive, but the auxiliary method we're going to use. So we need a scratch array so this all works. And then we actually call the auxiliary merge method. And then when we do cleanup to copy all the values from B back to A, which is where they're expected. So let's look at this auxiliary method. First, we determine are both subarrays empty. If one of them or more are not empty, we need to proceed to make sure that they're merged in. Then what we want to do is it's worth it to take the time to determine which is the larger subarray so that we are guaranteed at least a fourth of the values in the first one, or if we pick the midpoint of the larger of the two subarrays, then we're guaranteed at least a fourth of the values are there. And so quick swap, very, very quick and easy. Then we pick the midpoint of that larger section, then we get the actual value of it. And once we do that, we can utilize basically binary search to find how many values in the other portion, the smaller portion, are less than or equal to x. And then we can calculate where x is going to go, and then we assign it to the B array. Notice in the code here, this is the only place we are assigning to the B array, and it's only a single value. But so that's just amazing to me that it works as efficiently as it does. And then once we have that in place, we can then spawn off a thread to tackle all the values that are less than x, and spawn off another thread that are greater than or equal to x. And then we need to sync up to wait till they're done, and there we have it. We have multi-threaded Mergesort. Thanks for watching. I hope you enjoyed that.